Good morning students. In today's video we are going to see regarding the development length. So let us see now what do we mean by development length. So generally when we are going to design any RCC structure, we assume that there is a perfect bond which exists between the concrete and steel. That means there is no slippage. We assume that there is no slippage. So what all forces we are going to apply or which is going to come on that concrete, it will be transferred to the steel. So steel, it is going to take part in taking the load. So while designing or analysis, we assume one of the assumption is that there exists a perfect bond between the concrete and steel. So the grip of this reinforcement and the concrete due to adhesion or bearing is termed as bond. So the grip what we have between the concrete and reinforcement, that we call it as a bond. The next is the length of reinforcement embedded in concrete so that it can develop the stress by bond is termed as development length. That means we are going to have certain length of reinforcement which is embedded in concrete. So it is going to develop the stresses. So that length which is embedded in the concrete, so that is called as the development length. So now how to calculate this development length we are going to see. So let us see how to calculate this. Let us try to have this formula, that is development length in tension. So what we do, let us assume we are going to have one bar now. So let us assume that we have one bar which is of diameter phi. Then next, which is what you can say embedded in concrete. So you can see now this is one concrete surface we have. So we have one bar of diameter, what you can say phi, which is embedded in concrete. That means which is inserted in the concrete. The inserted length of the bar, let it be LD. LD is nothing but the development length what we have. Then next what we do, we will try to apply a force F so as to we'll apply force F to pull this bar. So whenever we are going to apply force F, what pull we are going to apply, then next what happens is there is a stress, bond stress, which will be developed. So that we can call it as tau BD, that is average design bond stress. Whenever we try to pull this bar outside, so there is a stress developed. So that is tau BD, that is average design bond stress. So what we can do is that what is the development required, so that can be calculated based on equating the strength of the bar and the bond resistance of concrete. So based on this we can calculate. So if you see this once again, let me tell you. So tau BD, this is nothing but whenever we are going to apply a force F, so there develops a stress tau BD, that we call it as average design bond stress. Then next phi is nothing but the diameter of the bar. Then next is sigma s, that is nothing but the working stress in the bar, and LD is nothing but the development length. This is nothing but the development length which is embedded in the concrete. So now how to calculate the development length? Based on the concept that we are going to equate the strength of the bar and the bond resistance of concrete. So based on this we will try to calculate the development length of the bar. So now how to calculate this strength of bar, let us see. So what we can do, strength of the bar, so that will be equal to pi by 4 into d square. This is nothing but the cross sectional area of the bar multiplied by the stress. So we are going to get the strength of the bar. Then next is the bond resistance of concrete force. So what we can do is that we can calculate this pi into phi. So we are going to get the circumference multiplied by development length LD. This is nothing but total length what we have multiplied by the stresses which are going to develop around the circumference of the bar for a total length LD. So therefore this is nothing but the this much resistance we are going to have, and this is nothing but the strength of the bar. So this is equation number 1 and this is equation number 2. So if you are going to equate both these things, that is equating equation 1 and 2, that is this pi into phi into tau bd into ld. So this we are going to equate it to equation number 1, that is this pi by 4 into phi square into sigma s. The next our aim is to calculate this ld, so therefore we can bring it this side. So this will be gone somewhere here, this we are going to have it somewhere here. So therefore what will be remaining now, 1 5 will be remaining, which is being written here. Sigma s we have will be written here. The next is tau bd we have, which will be written here, and this is 4. So remaining will be this much portion we are going to have. So based on this equation, what we do, we can calculate the development length, that is equal to phi, this is nothing but the diameter of the bar, sigma s, this is nothing but the working stress in the bar. The next is tau bd, that is average design bond stress, so that is equal to ld. So ld is nothing but the known development length of the bar. So based on this formula we can calculate the development length. So this is also this is also given in the code book. Let me show you in the code book they have given regarding the development length of bar. That is, you can see development of stresses in the reinforcement, how to calculate the development length of the bar. This is being given in the IS 456 2000. LD, that is development length LD, is given by phi into sigma s divided by 4 into tau BD. So where phi is nothing but the nominal diameter, sigma s is the stress in the bar, tau BD is the design bond stress. So now how to get this design bond stress, that is given in the table 26.2.1.1. So you can see here, this is the table 26.2.1.1, that is design bond stress in limit state method for plain bars in tension. So if we can see, they have given the different grades of concrete, M20, 25, 30, 35 and above. So for that they have given the value of tau BD, that is design bond stress. So for M20 it is 1.2, for M25 it is 1.4. Similarly they have given for M40, that is 1.9. So this is what they have given. Then next is, this is the formula what we have, and this is the table just now what I had shown. Then next is what happens is, this is for a plain bar. If you see the table, they have given it up for plain bars. Then next we are going to use deformed bars. So if you are using deformed bars, these values shall be increased by 60%. So that also they have given, if you remember, see this, for deformed bar increase by 60%. Then next is, if you are going to use the bars in compression, this value has to be increased. For bars in tension shall be increased by 25%. So if you are going to use bars in compression, the value of bond stresses for bars in tension shall be increased by 25%. So what tension value we are going to get? So if you are using HYST bar, you have to multiply by 60. Above that we have to apply increase by 25%, that is deformed bars in compression. So that they have given in the IS 456. Then next is, if you are going to use bars which are bundled in contact. So same again in the further clause here itself, they have given bars bundled in concrete, they have given these things. So let me show you. So the development length of each bar of bundled bar shall be that for the individual bar increased by 10% for 2 bars. So what development length we are going to have for a single bar, so that has to be increased by 10% for 2 bars. If you are going to use 2 bars, bundled bars, then it has to be increased by 10%. And if you are going to use 3 bars, it has to be increased by 20%. And if you are going to use 4 bars, it has to be increased by 33%. So this is the bars bundled in concrete, which is contact, so which is being given in IS 456 2000, that is clause number 26.2.1.2. just now what clause I had shown, 26.2.1.2. Here they have given what just now what all things I have said, it is being given here. Then next is that anchoring bars in tension. So what happens is that when we are going to use deformed bars may be used without end anchorages. Without end anchorages we can use, provided we are going to have development length is satisfied. If development length is satisfied, so without end anchorages also we can use the development what can say deformed bars. Then next is if we are going to provide a bends, so the anchorage value of the bends shall be taken as 4 times the diameter of the bar for each 45 degree. Right? If you are going to have one bar which is being what you can say bent at an angle of 45 degrees, then next we have to use as 4 times the diameter of the bar. So for 90 degrees it will be 8 times the diameter of the bar, and for 130 degree it might be 135 degree, it is 12 times the diameter of the bar, subjected to a maximum of 16 times the diameter of the bar. Then next is the hook, what we are going to provide these hooks and all. So if it is a 90-degree bend, you may have 8 times the diameter of the bar, and the hooks, the anchorage value of standard U-type hooks shall be equal to 16 times the diameter of the bar. The next is regarding this syrup and all, 26.2.4 they have given regarding these things. Then next let us see one problem, how to calculate the anchorage length of bars when it is being used in tension, when it is being used in compression. So we are going to take one example in which we are going to take one mild steel bar which is of diameter 5, and we are going to have concrete of grade M20. So now what is the aim? They have asked us to calculate the anchorage length in tension and compression. So first let us take this tension and let us try to calculate the anchorage length or development length in tension. Then next is let us calculate this design stress sigma s, that is equal to 0.87 into f of y. So as we are using mild steel bar, f of y value will be equal to 250. So 0.87 of 250, that will be equal to 217.5 Newton per mm square. Then next comes is tau BD, that is nothing but average design bond stress. So that is being given in the code book itself, that is average design bond stress tau BD. We are having M20 grade of concrete, so therefore its value will be 1.2. So tau BD value will be equal to 1.2. Then next is we have one formula LD, that is development length is equal to sigma s into phi divided by 4 times of tau BD. So we will try to keep this phi as it is. Then next is sigma s is 217.5. Then next is tau BD, just now we have seen from the table it is 1.2. If you simplify this by keeping phi as it is, so it is approximately 45.3, or approximately it is 46 times the phi, that is nothing but the diameter of the bar. So when we are going to use a mild steel bar in tension, so development length will be equal to 46 times the diameter of the bar. Then next, similarly, if you are going to use it in compression, then next what should be the LD value? So summation of sigma s is equal to 0.87 f of phi, that is 217.5. Tau BD, what they had given? So for plain bar they have given, and they have given certain clause for what you can say deformed bars. And for other types of bars they have given, just now I had shown you, you can see here they have given for deformed bars it has to be increased by 60%, and for bars in compression, so it has to be increased by 25%. So for tension we have calculated, now we are calculating for compression, so that value has to be increased by 25%. So therefore tau BD, that is nothing but average design bond stress, value is 1.2, just now what we had seen. So it has to be increased by 25%. That means if you multiply it by 1, it is nothing but 100% what we have. So we are multiplying it by 1.25. 0.25 is nothing but 25% extra. So 1.2 multiplied by 1.25, we are going to get it as 1.5. So this is nothing but bar in compression. Again same formula, LD is equal to sigma s into 5 divided by tau BD, that is 217.5. So we'll keep this diameter of the bar as it is, divided by tau BD. Tau BD is 1.5. If you simplify, we'll get answer as 36.25 times the 5. So we can take it as 37 times the 5. So this is the development length when we are going to use in compression, and this is nothing but in tension when we are going to use a mild steel bars. Similarly, if we are going to calculate for M20 grade of concrete for different grades of steel, that is Fe250, Fe415 and Fe500, for tension and compression, we are going to get values somewhat like this: 46 times the diameter of the bar, 37 times the diameter of the bar, just now what we had calculated. Similarly, if you calculate for Fe415, we will get it as 47 times the diameter of the bar and 38 times the diameter of the bar. And when we are going to use Fe500 in tension, it will be 57 times the diameter of the bar, and in compression it will be 46 times the diameter of the bar. So these things you can remember, or you can use that formula so as to calculate this value. So just now what we have seen, it was for Fe250, that is mild steel bar. So further if you want, we can do calculation for this and this. Then next we will take another example of a bundled bars now. So calculate the anchorage length of a group of 3 bundled bars. We have 3 bundled bars in contact and of equal diameters in tension. Concrete grade is M20 and we are using mild steel reinforcement. So development length formula is sigma s into 5 divided by tau BD. So sigma s is nothing but, just now we had calculated in the earlier problem also, for mild steel it is 0.87 into 250, that is equal to 217.5. So we'll keep this diameter 5 as it is. Then next is 4 times of tau BD. So tau BD value is 1.2. So therefore it is 46 times the diameter of the bar. This is for a single bar. But as in the question they have said, we are going to have 3 bundled bars. So when we are going to have 3 bundled bars, so we are going to increase it by 20 percentage for 3 bars, 10 percentage for 2 bars, and 33.3 percentage for 4 bars in contact. As we have 3 bars, we have to increase this value by 20 percentage. So therefore now development length will be equal to 46 times the diameter of the bar. This is nothing but for a single bar. So this value has to be increased by 20 percentage. So therefore 20 percentage is what? Multiplied by 1.2. This 0.2 is nothing but 20 percentage extra. 1 is nothing but 100 percentage we have of this value. So we are multiplying it by 0.2 extra, that is so as to increase the 20 percentage value. So if you multiply, you will get answer as 55.2 times the diameter of the bar. So you can say that LD value is equal to 56 times the diameter of the bar. So generally in the side, this is what they say.